All right, good morning, everybody. Welcome back for our final day, and it's an exciting sort of a mini symposium within the big meeting, focusing on the future of artificial intelligence in medicine, and mainly on cognitive and deep learning, but we're going to also have some interesting miscellaneous topics. So I've on stage with me the four very smart people, but also good friends of mine who are going to talk about the future. I think they're particularly poised to talk about the future. So just a quick reminder, based on your questions, a lot of the slides and abstracts are going to be uploaded, and we'll keep the app going for a while. And one question was, can we transition the app into some workable blog? And we're absolutely going to consider that, and just keep the conversation going after this meeting. I think there's a lot of enthusiasm, a lot of passionate people. We absolutely want this to be an educational tool for until the next meeting. And speaking of which, we're seriously considering having this meeting about the same time next year, probably here also. And you know this by now. Okay. So basically this morning we're going to have an opening session, sort of a dialogue with a few slides talking about the future. And then we'll take a short break, and then we'll go right into the cognitive computing session. And then a longer break followed by a sort of a nice highlight of the meeting, whole big session on deep learning, which is what everyone's talking about these days. And then we'll have a final takeaway and session with all the speakers on stage. So a few cartoons about AI tomorrow. So this is AI of the past. And here, if you can't read it, it says, "My report on your desk, your shoelace is untied, and tomorrow's your wedding anniversary." So I don't know when this cartoon was done, but we're kind of there already, right? So, all right, so again, I'm not going to delve into the topics that you'll be hearing about the rest of the morning. Just thought I'd put down some personal perspectives on the AI of the future. So I want to pay tribute to Spiro Mouzes, who's in the audience, my intellectual partner here in Orange County, about how to look at data and databases. So one of the things that I noticed in healthcare, we talked about data quite a bit a couple of days ago. You know, we're still in sort of the 1960s, 70s in terms of even the database. If you think about a relational database, so many sectors in life are not really in the relational database format any longer. We need to start thinking about how do we transition healthcare into graph, and as Spiro says, even a hypergraph database format. So the earlier we start to get to be acquainted with a different database, I think the easier it's going to be for the AI methodologies to take place. So point number one is, let's think differently about data and databases for the future of healthcare and artificial intelligence. I think another aspect I'd like to raise, and having spent the last 5 years with many, many smart data scientists, is there's a lot of discussion about big data, large data sizes. So we're heading into that upper right corner quadrant where there's big data and lots of samples and lots of data. But what about the lower left corner quadrant? I think that's also important for both data scientists and clinicians to appreciate in terms of artificial intelligence in medicine. So just curious, how many people have read this book, The Laws of Medicine, by Siddhartha Mujari? So it's about 3 basic laws, and one of them is about outliers. So outliers, in his opinion, and I totally agree, can teach us perhaps even more than the population. So we need to appreciate what outliers can do. So I'm going to suggest that we start thinking about the lower left quadrant with small data sizes and not too many samples, because in fact that's the nature of medicine, right? Sometimes we have a rare disease, and that's where one-shot learning is particularly meaningful. So one-shot learning, if you haven't heard about it, is under the umbrella of deep learning, in the sense that we can do pretty sophisticated algorithms with just a few samples. So it's called one-shot learning. And that's relatively new. So I like this cartoon about one-shot learning. So the gentleman says, I believe that this time we really were successful in implementing a one-shot learning algorithm in our robot. Right, robot? And the robot says, what is one-shot learning again? So, okay. The other aspect is deep learning. We heard about deep learning and DeepMind, and Jack is here from Google. And what's really impressive about DeepMind and AlphaGo and Google is it's really kind of set the bar even higher for AI and the expectations we should have in medicine. And this is a graphic from the Nature article talking about how sophisticated this is. So this is not just deep learning, even though that's pretty sophisticated. And deep learning now has potentially more than 100 layers of neural networks. So it's already gotten pretty sophisticated and, mimicking the brain, not duplicating the brain. But we're talking about a totally different way of using this technology. And it's a beautifully written article in Nature, even for someone who's not well-versed in that kind of language. Talks about how sophisticated this is in terms of mimicking a human and making decisions with huge sample sizes and only for the near future, not necessarily for the long-term future. And that's, when I read this article and heard what DeepMind is doing, the first thing I thought of was, this is exactly analogous to what people do in medicine. You have huge data sizes you have to manage. At the same time, you don't know what the mid and long-term future is going to be. So I think this is very impressive. And also, we're well set up for deep learning and its most sophisticated form with AlphaGo in clinical medicine because of all the layers that we have to deal with for decision making, and also for precision medicine in its purest sense. So I try to come up with a word that will symbolize each sort of the past, present, and future. Talked about concatenation in the past, which is just a series of eras. The present, I can think of convergence. We're all here together for the first time for many of you. I think in the future we have to think about convolution. I have to thank my math friends for teaching me this concept. So convolution, it's probably easier to just show rather than describe it, but you basically have two functions, mathematical functions. You can pretend that F is perhaps medicine, and function G is data science or just math. And you want to create a third function so that it will become literally a totally different function and benefit greatly from that. So we need to become a third function. We can't say, label ourselves as clinicians or data scientists. We actually have to, more than converge, we actually have to convolute and become one when we approach AI in medicine. Sorry if that's a little too much math for you early in the morning, so we'll move on. And you thought I ran out of metaphors, but I have another one. Okay. So AI is the orchestra, and I think we all need to be the conductors. So there's, the machines are ready for us. We really need to get on board and make a big difference. And I had very encouraging conversations with some of the clinicians, particularly now interested in knowing about R, Python. R was just a letter for me 5 years ago. Python was a big snake, So there are new programming languages that we all need to embrace and learn to do this together. So again, it's not about the robot. It's about creating a new energy source to illuminate the dark areas in medicine. So some of the takeaways from yesterday I wrote down. We could use an autocorrect for biases, although there's an inherent danger in that too, so have to be careful with that. I think education AI is needed for everyone in healthcare and medicine. Deep learning still need big data sets. So there's this misconception that deep learning can do it all, but you still need good data sets and databases. There needs to be a sense of urgency. I totally agree with Randall that we can't just be meeting and talking about this and getting excited. There needs to be a sense of urgency that we need to get this done in our lifetime. And the startups need to work closely with clinicians. We can never say that enough, I think. So thanks to Brett on our team, this is the word cloud from all the comments and questions you've made. So we'll post this on our app and website, so you kind of know what we've been talking about. This is just a wonderful way to look at all the things we're talking about. So, we've had sunset breaks, right? How many people here know about the green flash? Okay, quite a few of you. So it's an optical phenomenon that occurs as the sun is just going below the horizon. So I've been busy, I haven't been watching the sunset, but was there one in the last few nights? Okay, no, okay. So I think this is very symbolic of AI in medicine, because it's sort of like once you see it, you're gonna keep looking for it and really think it's a magical phenomenon. And I think I would encourage those of you who are not quite believers in AI in medicine just yet, to really be patient and look for that moment, defining moment, that you're gonna say, this is gonna be around for a while. And it takes a village to do this. I used to show this picture of the ocean, and you can't see anything other than water. But if you look very closely, there is a village of surfers. And you can probably see it out there during the day. It takes a village, even though it's very daunting. If you could think about data and databases in healthcare as the ocean, it's daunting. There's a tsunami coming, potentially, of data. But if we hang together as a village, and you notice for the surfers, you don't know who is a data scientist or who is a clinician. So we should all become sort of data surfers in AI and medicine. And then once you're inside, I've never seen this myself, but I'm not good enough, but it's amazing what you can see inside. And this is an actual photograph that was taken. You can imagine this is a life-transforming type of picture that you can see inside this water tunnel. And lastly, I think the best thing about AI medicine, and I always say this, is it brings back more compassion and human care. And that's the part I'm most excited about. So hopefully with the help of our data scientist friends, we can retransform medicine into one that has compassion, where the human touch is still the most important thing. So with that, I thank you with everything that's happened so far and for your words of encouragement. So we're going to go right to our distinguished panel. Okay. I think Jeremy, you're up first. So tell us how you're looking at future of AI in medicine.
So thanks, Anthony. I just really wanted to focus initially on why this matters. And the reason this matters is shown in this slide. This is something that was produced for the World Economic Forum. And it shows here the number of doctors in Nigeria. If you look at this same chart for any developing country, whether it be Indonesia or India or China, they all look the same. This shows how many doctors there were in Nigeria in 2012. And this shows how many we can get to by 2030 at the current training rates. This is the number that Nigeria needs to have the same health outcomes as we have in the West. And so this difference here is a 12x difference. It will take 300 years to train that many doctors. So at a cost of $51 billion. So as I say, this chart is identical everywhere in the developing world. This 12x varies between about 10x and 18x. So what's this got to do with AI in medicine? Well, a very large piece of this is taken up with answering those two questions. What's wrong with this patient and how do we make them better? It was realizing that answering that question can be done using a data analytic approach, which led me to leave my job at Kaggle and move into medicine about 3 years ago, to basically look and see what would it take to solve this gap, or to solve a lot of this gap by taking advantage of the kinds of data analysis techniques I've spent the last 25 years learning and applying. And what I learned was that we can do a lot. I've spoken to hundreds of physicians and academic medical folks and hospital administrators over the last few years. And I've realized that on the whole, the data we need already exists. The technology on the whole we need largely already exists. So what are the challenges we're still facing? There's a couple. One is culturally. I found it very difficult to get doctors and hospital administrators to unlearn the assumed constraints that they had. So my particular starting focus was in radiology, because radiology is already so well digitized, it's great low-hanging fruit. And as somebody looking to apply deep learning to radiology, it seemed obvious to me that the right way to do it was to take one data set which has lots of medical images and one data set that has lots of afflictions and interventions that have been tried, and basically using deep learning correlate the two together such that for any input imaging, you would basically say, this is what's wrong with this person and this is how to make them better. To a classic medical expert, this seems really weird. The classical medical expert would say, no, we would take a single type of imaging for a single part of the body, for a single affliction, and then have lots of people build a model of that affliction for that part of the body using that particular kind of diagnostic data set, which seemed really weird to me because for a machine learning person, that's entirely pointless. In fact, if you want me to create a model of malignancy, of tumors in the lung using CT scans, you will get a better one of those if you let me look at every kind of medical image for every kind of the body, for every kind of affliction, because deep learning can learn from all of the types of images. As Anthony said, our models now have over 100 layers of neural networks. Each layer is learning more about how the body works, how it responds to disease, how it reacts to different interventions, and so forth. So one of the challenges was just getting people to expand their minds to the idea that you can solve all of the diseases at the same time. And hopefully later today we'll hear from Joel Dudley about some experiences with trying to do exactly this in a hospital setting. The second problem was the lack of integrated data sets. I found places where the data existed, but what we really needed was stuff like what John and David from VPICU at CHLA have shown, which is a long-term sequence where we can say, these are all the measurements done to this patient, these were the interventions used on this patient, this is the outcomes that happened to this patient. Because once you have that, you can feed it into a recurrent neural network and basically answer questions like, okay, what would happen if we gave this drug to this patient at this time? And better still, what would be the best thing to do to this patient at this time, and then what would happen next? So although the data exists, on the whole, within a single hospital, it exists in many different places, and then of course it exists across a lot of different hospitals. So one of the big challenges is, for example, in pediatrics, where I know Anthony is working to fix this problem. Diseases look very different at different age kids, and also kids get different kinds of problems to adults. So to actually solve this in the pediatrics world, it's really important that we pool across multiple hospitals and within a hospital across imaging, genomics, lab tests, other types of pathology, and so forth. But as I say, basically the data exists, basically the technology exists. At this point, it's kind of a combination of regulatory, politics, culture, and a certain amount of just hard work.
Great. Wow, 7 minutes kind of sets the tone for the future. Jack, you're at Google, so you guys ready to take this on for the future? And do you think there's enough storage, enough analytics to be at least one of the leaders in this field, right? That's what you're aiming to be, so. There's a microphone over there, sorry.
I think those of us who work in healthcare and in computer science agree completely with Jeremy. I think the lack of these integrated data sets is very, very frustrating for those of us who are trying to build learning models. I think probably every single clinician in this room have been hampered by things that we know we should be doing, but whether it's processes, whether it's culture, inside the provider environment, we haven't been able to do the right things. I think these are all problems that are very human created and is very, very solvable. I think part of the solution is to build technology. I think a lot of it, as Jeremy mentioned, has to be us coming together as a community to try to tackle some of the non-technological issues that came up.
Yeah, so I think one of the takeaways from this meeting perhaps is, despite all the portfolio of AI methodologies are actually fairly mature, we still need human beings to make it all happen. And as ironic as it is, but it takes humans to do this. So, microphone please.
I just wanted to correct one of your takeaways from earlier, which is that deep learning needs lots of data. That's actually empirically not true. It's not true if we take advantage of something that Kurt talked about in an earlier session, which is something called transfer learning. Once you've used a lot of data, like Google and others have, to do totally unrelated things, like recognize pictures of cats from pictures of dogs, we can leverage many of those layers of those 1,000-layer neural networks to teach us the difference between a malignant tumor and a non-malignant tumor. And then once we've learned the difference between a malignant tumor and a non-malignant tumor using a CT scan, we can then take advantage of hundreds of the layers of features of those neural networks to teach us what they look like in an MRI. So, for example, we only needed 1,000 examples of patients with malignant lung cancer in order to build a very accurate model of malignancy.
Yeah.
So, and the reason I wanted to mention that is because I don't want anybody on the audience to think they can't be involved in this because they're not Google and they don't have enough data. Any even medium-sized hospital has plenty of data.
So sort of like mimicking the human brain, a seasoned radiologist may not need a lot of memories of all the scans in the past to be able to function.
Right, yeah.
So,
These multi-layer networks
But I meant-
work very similarly to
Right.
intuitively how the human brain would think of it, which is you have varying levels of semantic complexity. You know, at the start, it's like, I can recognize an edge and a gradient, and then I can recognize a corner and a circle.
Yeah.
And a few layers up, it's,
Yeah.
I can recognize how the body reacts to disease, and then later on, I can recognize how the body reacts to disease and how that looks like under an MRI, and so forth.
So, but is it fair to say that early in the process of learning a new disease or a new image, they still need a reasonable data set, right? For deep learning.
Right, but
I think that's what I was
right, but that's
implying,
now been done.
Yeah.
So you
Yeah.
would never want to start with an empty network. You would always
Yeah.
want to start with somebody else's pre-trained weights.
So since we're on the topic, what do you think about, what's your opinion on one-shot learning that's creating some attention in terms of another approach to this?
Yeah, so one-shot learning is just a special case of learning with small amounts of data, and we have so many examples to know it works. For example, at Kaggle, we had a competition on one-shot learning for recognizing gestures for an Xbox. So we had a single video of people doing like a stop sign or a come or whatever, and then the test was, can you recognize that same gesture in a test set? And the results were pretty accurate.
Okay.
And of course, it was done by leveraging these pre-trained models on other domains and then doing transfer learning.
Thanks, Jeremy.
So I want to actually hedge some of what Jeremy just mentioned and actually sit between what Anthony mentioned and what Jeremy mentioned. So we talked about the diabetic retinopathy paper, and that worked on quite a lot of images. And as Jeremy also mentioned, we also pre-trained it using the data on Inception Free. So I want to mention two things. So one is Google, and not just Google, many of the folks working in this deep learning community have not just open sourced the code to the deep learning, but we've also open sourced some of the pre-trained models. So in the case of ImageNet, we've open sourced the pre-trained models so you can learn on top of it. You can build applications. And we also have seen some examples where you can take thousands of images and the model can learn pretty well. On the other hand, I think we've seen that at least what we've seen of pretty good models are we are seeing that models are performing in the 85, 90 percentiles, significantly better than what you might expect. On the other hand, I think in many cases, medicine expects much higher numbers than the 85, 90% that we can get away with in the consumer app space, right? A specificity of something like 90% can easily send millions of patients who were just getting a screening test into secondary testing, which might potentially cause a lot of problems. So we're still caught in this space where we think the models can be significantly improved by transfer learning, but it would be very, very helpful if even bigger data sets are built so that much more accurate models can be learned.
Interestingly, one of my learnings, which I was pretty disappointed by in the time I spent in medicine, was we would have to be twice as good as radiologists,
Yeah.
and before people would even begin to be interested. But even then, it was very hard to know if you were twice as good as radiologists, because the baseline of how good are doctors, there's fuck all data about that, frankly. And so when people say, oh, 85% is not good enough, it's like, okay, well, show me a really accurate measure of how good doctors are at this.
Yeah.
And of course, the other point we've kept on talking about is this is about then giving a doctor this as an additional piece of information. So how much better would they be if they had their, however accurate they are, and we generally don't know, plus the 85%? You know, the combination is going to be amazing.
Yeah, I thought it was interesting that everyone should really check out the JAMA article that just came out, and there's some really interesting ROC curves. It's almost comical, but there's one solitary ophthalmologist that's still way ahead. He must be really worried, he or she, I should say, must be really worried that Google's catching up pretty fast. So, Jack, tell us about what your perspective is on future of AI in medicine.
So I'm going to be much more general and much more forward-looking. So I think we talked a lot about the potential. Other slides gonna.
Slides, please.
Can I have the clicker?
Yeah.
So I want to caveat this with that this is my personal opinion and not the opinion of Google. This is especially true when we talk about the future, where I am almost positive that I will be wrong. So I don't want Google to be attached to it. So I feel like there are three very interesting hopes that I have for the future of AI in health. One is on Ensemble connected health devices, which I'll talk about in a second. The second is on up-leveling physicians, and the third is on empowering patients. So what do I mean by Ensemble devices? So we talked a little bit about wearables yesterday. So there are a lot of wearables, there are a lot of connected Internet of Things devices these days. And most of them are right now working in very separate domains. There's a separate app for each of them. They perform a very specific function. You have to set up these rules by yourself. So right now, most of these devices theoretically are talking to the internet, but they don't really talk to each other. Even in the cases where they start talking to each other, it's not clear what the group of devices should do. So we're very early in the process of humans setting up those rules and trying to figure out what these things can actually achieve. So one of the things that I think on the consumer side we're already starting to move towards is grouping these devices and actually starting to add intelligence on these devices and actually get these devices to help us fulfill needs as opposed to just doing these one-shot-off tasks. So let me talk about a very brief consumer story that might lead to an example. So you can think about a new parent trying to put a child to sleep. And potentially you have a number of IoT devices that will figure out that this is perhaps a similar time of the day in which the baby usually put to sleep. It senses accelerometers in the baby and accelerometers on the mom that notice that both of them are essentially having less activity, and it might even notice that the car is in the garage, and it recognizes that essentially it's time to put the baby to sleep. Once the baby is sleeping, maybe a number of devices, a number of sensors figures out that the baby is asleep and we need to keep the baby asleep. So it might dim all the lights that are in the house. It might quiet all the devices that normally makes a lot of sound. And in fact, it might actually actively suppress devices like vacuums and other devices that are going around the house to try and keep the baby asleep. And then you can imagine that if the baby awakens, there are devices that would help notify the parents. It might be on the TV that they're watching at the moment. It might be on the phone. It might be on different types of devices. And that's a lot of devices that are all shared a common intelligence, all trying to fulfill an actual need. In medicine, I spent a lot of time working in the ICUs. We theoretically have an Internet of Things set up already. So we have lots and lots of devices, lots and lots of things already being uploaded to telemetry, most of which we only pay attention on screens as they fly by. And frankly, most of them we don't do a great deal about as an integrated ensemble. And it would be great, and I think this, many ICU physicians' dream is to have all these devices actually start working together. And there are systems already starting to do that. Philips is building essentially closed-loop ventilators. J&J, unfortunately, worked on Sedasys, which was a closed-loop anesthesia machine for colonoscopies. That didn't do well in the US, but different medical device manufacturers are already trying to connect these devices, use the output of one of these sensors as the input of the next, and try to actually do closed-loop operations for physicians. That is a big hope that I hope the industry will actually open a lot of standards, start to connect these devices, and layer AI on top of it to achieve some of these outcomes. The other, a second point that I made was I think up-leveling physicians would be very, very interesting. There's right now a number of tasks that are being done by physicians. Jeremy mentioned, diagnosis is one of them. I think in particular, many of the imaging modalities, whether it's ophthalmology, whether it's radiology, dermatology, right now are just going from an image to a diagnosis. And those things, I think, are very apt for deep learning to do, and it's time for us to help those physicians and to up-level their capabilities. So this is not our product. I'm extremely impressed and amazed by this product. This is Microsoft HoloLens. I've seen many videos of it. I don't know how far they've actually gotten along the process of creating this, but they demonstrated basically the ability to stack 3D radiology in real time, and you could actually see the video on YouTube, and really help the physicians and medical students look into the body, and you can imagine things, everything going from planning of surgeries to really understand what is going wrong in a patient's body, and not just looking at an image and making a diagnosis. The other part that I hope that AI will really help is in empowering patients. So right now, 1 in 20 Google searches are health-related. And I'm sure you guys probably have all searched various things on Google. These are the type of queries that we see very frequently. So people are searching for everything from conditions to symptoms to trying to figure out what treatments they should take. And right now, I think we do a fairly good job of reporting what the web shows. Whether that is a good thing or a bad thing, you guys can judge for yourself. But what would be great is, and this is another representation of the various things that we're looking for. There are lots of folks looking for things like home remedies. But what would be great is that we could start to use some of that signal to do much more interesting predictive results. So this is also from Microsoft. His work was recently very referenced on looking at Bing search results and being able to predict the onset of pancreatic cancer before the patients even knew it. So Eric basically looked at the sequence of search terms that happened on Bing and looked at some of the symptoms that they were able to classify, and then eventually realizing that the patient started looking at pancreatic cancer and treatments of pancreatic cancer. And he was able to figure that out from the search query. So I mentioned in previous talks that one of the really powerful things that help deep learning models, and Jeremy also referenced this, is data sources that are very disparate, because very similar data sources starts not providing as much new information as possible. And in this case, Bing has been very interesting in using these type of data sources to try to help different models. And of course, this is Amazon Alexa. I think many of you guys have probably already seen Alexa, Google Home. Microsoft recently came out with a device, I think yesterday, 2 days ago, starting to do essentially a smart assistant. Right now, the applications are still pretty rudimentary. We help with things like time, setting timers, potentially ordering pizza. But Alexa have started to venture slightly deeper into the space, and they partnered with Boston Children, looking at perhaps Alexa can answer a few questions about your child getting sick. If you actually try and use the feature, it's not the most refined feature at the moment. It's a very, very long, drawn-out discussion, but it's great that I think a lot of the tech giants and a lot of the startups are starting to move towards that type of user interface. to start getting patients really engaged and using AI to help in that process. And that's basically what I think and what I hope will happen in the future. I just want to make a quick plug for our team. So Google Brain has a brain residency program. So for those of you who are interested in deep learning, we basically bring on external folks into Google for a year to work with them on a project and to teach them deep learning and then send them back out to their respective companies, university campuses, et cetera. We have been running this program for around 3 years, and in the last year we had around 100 folks come and learn deep learning and learn exactly what we do in-house. So if any of you are interested, please Google Brain Residency. Thank you.
That's phenomenal to have a full residency program. Do you take 58-year-olds in the program?
We do. We actually, last year, we ranged from having senior deep learning experts to actually someone who dropped out of college who has very little programming experience. So we're looking for folks either with a lot of experience who want to see what Google's doing, or with very little experience but comes from fields that typically haven't used deep learning to expose both groups.
Like healthcare?
Yes.
Yes. So I'm going to extend what your proposal was in terms of search queries for different diseases. What about in the future that not only are you going to be the patients able to get on a search query for a lot of terms on the internet, but actually go into a national, international patient repository of information, EHR, basically. Do you see that happening this decade, potentially?
That has always been the hope. I think it's been a very difficult hope to achieve. I think many of us who've worked in global health and such have tried to build global, at least vaccination record repositories. Yeah. I'm sure many of you, especially even those of you who have young children, will have realized we're still doing vaccination records on paper. Some hospitals have started doing it electronic, and that's frankly pretty crazy. We haven't, as Jeremy mentioned, had a lot of success, even when the technology is clearly very doable, to get the different policy folks and the different, frankly, people in the process chain to do it. I think your effort on getting the different children's hospital is an amazing effort, and my hope is that as more of these efforts mature and it becomes very clear that the learnings that come from these collaborations are well beyond what any one of these institutions can achieve, that these things will start accelerating significantly.
Well, what Jack is talking about is we're trying to create an alliance of children's hospitals, and it's called International Society for Pediatric Innovation, basically to push big ideas and big goals as an alliance of children's hospitals. We have about 30 charter members, about 60 hospitals interested in being part of this group. All right, so one of the best things about 5 years at Stanford, getting education, is you meet amazing people, and I'm still old school, so even though some of my courses were virtual, I will always fly up to Palo Alto and insist on meeting the professors face to face. So Tim had to put up with that on a Saturday morning, but really amazing to have met him and got to know him, and one of the progenitors of cloud computing in the early days. So Tim is particularly, I think, insightful on looking at the future of healthcare. So I've invited him to join us on this panel. So Tim?
Yeah, I should extend that story. So yeah, I teach a class at Stanford that I have probably 75, 85 kids that are on campus, and so about 10 of them are remote. And so I get this email, I'm a little old school and I want to meet the professor. And I went, well, okay, right? So I arranged breakfast. I'm sitting there, and then Anthony walks in, and I go, well, I guess not the regular student. If you haven't heard the story of him going back to school, it's pretty impressive. I love telling this story because it's never too late for any of us, right? So I come at this, I am not, even though I got a little healthcare thing, kudos there, I don't think of myself as an expert in this. On the other hand, I have spent a career in the world of enterprise software and business software, and so what I'd like to share with you is a little bit of my journey of why this intersection of cloud computing, data, deep learning, et cetera, is a particularly interesting space. So my background is I both I play an academic. I've taught at Stanford for a lot of years. In the old days, real stuff like computer architecture. These days I teach this seminar class mostly because I don't want to work very hard. But I also have had a career on the commercial side, and so I've worked a lot of years in enterprise software. Most recently, I spent about 6 years working at Oracle, working for Mr. Ellison, running what is today their $2 billion cloud business. So when I left, and I live in Silicon Valley, I started thinking a lot about the question of, well, what's next, right? And if you're at all familiar with enterprise software, we kind of have done this thing where we do CRM and ERP and e-commerce and all these sorts of applications. We deliver them on premises. We've moved them to the cloud. But functionally, there's not much new, right? And I'm like, was that it? We don't have any more creativity left? And the other thing is, because I've done a lot of work in cloud computing, about 6 years ago, I started teaching a class at Tsinghua University in Beijing. And I know the Amazon guys fairly well, and they gave me $3,000 worth of computer time. So I showed up in class and I said, oh, here's $3,000 worth of AWS time. It'll buy you a server in Northern California, Virginia, or Ireland for 3.5 years. And they all looked at me and went, yeah, so what, right? I've got a server in Beijing for 3.5 years. Why do I care? And I said, or $3,000 buys you 10,000 computers for 30 minutes. 10,000 computers for 30 minutes. And the question that I wanted to put in their head, and the question that was already in my head, was what the hell would you do with that, right? Because the step functions in the computing industry have been step functions of things which were never economically possible, now becoming possible. So about 2 years ago, I came at least to my own answer to these two questions and have, as I like to say, pushed all my chips in this whole area, which people are using the phrase Internet of Things, industrial internet, et cetera. I was lucky enough to get exposed to a bunch of the guys at General Electric and the work they're doing at GE Digital. And so I thought, well, if I'm going to do work, invest time and energy in this area, I better understand it. And so I thought, well, maybe the best way to do that is to write a book. So I started this project. We actually launched the book on the River Thames in June of this year. That's a cover of it. And I'm not going to go through the book, but let me just leave you with a couple of things that I want you to think about. So the first is, most of the work we have done up until now in the tech community has been focused on what I call the Internet of People. So whether that's, e-commerce, search, ERP, CRM, all these sorts of applications, it all basically believes that we're talking to a person, a human, a person, a people. And I inspire my Stanford students by making this amazing observation, which people are not things, and things are not people. And once you start to realize, and let me just give you a couple little things for you to think about. Most of all that's happened with us is, we get to type a little bit and move a mouse and click some stuff. If you want to think about machines out there, and I'll use wind turbines as an interesting case study. So wind turbines right now have 400 sensors on them, right? They have an amazing amount of data that vastly exceeds anything that we could deliver. Second of all, they can talk much more frequently. There are sensors on top of a coal mining machine that actually run at 10,000 cycles per second, right? The modern car, you may never have thought about this, actually has 25 gig of data per day. Now, none of it's sent anywhere, it just sits on the car. But once you start to realize that things are not people and people are not things, then why would the technology for the Internet of People work for the Internet of Things? And so I believe we're at a point, a juncture, and I get to talk later, so you'll get me more detail, but I think we're at a junction when there's going to be whole new types of technologies for the things themselves, how those things are connected, how do you collect the data from them, what are you going to learn from that, and then finally, what would you do differently? So that's the first thing. I want you to think about that we're at a juncture where I think there's going to be a whole new class of technology for the Internet of Things. The second thing I want you to think about is the data itself. We're pretty, at this stage, unsophisticated talking about data. We kind of just use the word data. And at least in my observation, I know this is happening in healthcare, but it's happening in steel manufacturing, it's happening in automotive, it's happening in semiconductors, is there's a tussle, a war between whose data is it. And at the end of the day, I think we're going to have to start to think about this differently. I started to talk to people about the idea that there's data from machines themselves. So if you look at a gene sequencer, that might be, you know, the laser power level, the chemical reagent level. And then there's gnomic data, right? Obviously, in this case, genomic data. And those two things, while obviously coming from the same machine, are not the same. And I think we're going to have to get more sophisticated about that and engage people both at an industrial level and at a public policy level in this whole conversation. 2. 3, and I was surprised to see Jeremy's first slide, so I'll just take that. So I have the opportunity to, I like to say, warp young minds at Stanford, right? So I don't know if anybody's thought about this, but the world economy is actually driven by developing economies, right? Developing economies are driven by population growth. The counterexample of this is Japan right now, right? It's been a stagnant economy for a lot of years. So what are the developing economies, right? The developing economies. Well, Southeast Asia, right? Latin America, Africa. You may not realize this, but Africa is headed to be the 3rd largest country in the world by the year 2040. It will be the India, China, Nigeria. 25% of the world's population is going to be in Africa in the year 2040. And so once you start thinking about that, you go, interesting. If I'm a developing economy, if I'm a developing population, what am I going to need? Well, I'm going to need the fundamental infrastructures, right? I'm going to need power, water, agriculture, healthcare, et cetera. Telecommunications. So I asked the technology community, I go, well, you know, would you, if you wanted to build a telecommunications network in Africa, would you go put up a bunch of landlines? And the answer is no, obviously, right? You'd skip ahead a generation and, you know, put in 4G, 5G, et cetera, et cetera. I think a similar opportunity exists across many of these other industries. How would you redo power? How would you redo agriculture? How would you leapfrog using technology to do this? And at the end of the day, and I'm going to have to borrow that chart. If you think about healthcare, you go, we'll never build enough medical schools, we'll never build enough hospitals, right, to do it, quote, our first world way. And I think the challenge to the community, to you guys, right, to the students that I have, I go, guys, look, you have to start to rethink this, right, and how it is that a new generation of machines might fundamentally change how we do these things. And so I want to leave you with that and encourage you to, if you have young people, to get them to think about this problem, because at the end of the day, I say, look, unless we all move to Mars, which I know there are people working on this project, but unless we all move to Mars, we are going to have to operate much more precisely on the planet. And the second point is, right, without doing this, the gap between the haves and the have-nots is just going to get wider and wider and wider. So the investment of time, energy, money into this whole area, I believe, is huge for the planet itself. So with that, I'll hand the mic. And I got done in exactly the right amount of time.
Yeah. Thanks. Thank you, Tim. One of the best things about putting a meeting like this together is you meet incredible people that you haven't known before. And happy to say I met Lorenz just a few days ago, and she's got a really great perspective. Since, you know, I gave every panelist here free rein of what they want to talk about for 10 minutes, and she's come, it seems like education, getting away with bias, and keeping an international scope for AI in medicine is particularly important. So I invited Lorenz to come and share with us her thoughts about the future of AI in medicine.
Thank you. So I'm going to try to see how that thing works. Good morning, everyone. So actually, for my day job, I build innovation functions for pharmaceutical companies. So not exactly the topic I'm going to talk about today. I'd like to take the opportunity of this talk to share how actually some people in Israel, with this beautiful organization, United at Salah, are using data to actually save life. So, hope it's the right button. Yeah. Well, this is a picture that could have been taken literally anywhere on the planet. This is a very common situation where an ambulance has a hard time reaching the scene of an emergency where help is needed. So why is that a problem? Well, simply because time here is critical. So the time between the moment an ambulance is sent to help someone and the actual intervention on that person is a determinant in saving life. So I actually try to pull some slides together for you guys on the average response time in the world in different cities. It's simply impossible. What do we take into account in here? There's no standard at all. So we're talking about the moment where the ambulance is being sent, where it actually leaves, when it's actually arriving somewhere. Is it arriving at the building, at the patient? We're starting to help the person. It's impossible to actually have statistics, but New York City has a gold standard for 10 minutes. Obviously, it's almost never happening. California had a standard for 8 minutes. They just raised it to 12 to 15 minutes because it's just not happening either. An ideal response time is considered to be 8 minutes, but it's almost rarely happening. And why is this important? Is because if you take cardiac arrest, well, in a few minutes, the brain starts to be damaged, and every minute count to help a person. So what is United at Salah? Well, it's a pre-ambulance, community-based service care that is being provided by volunteers, and these volunteers are civilians that are going through rigorous training, and they're empowered by technology and by data. So the volunteers are people, there could be any one of us, they're doctors, paramedics, but also any person who wants to go through training and to learn how to save life. We give these people what we call ambucycles, and the ambucycle is a motorcycle with all the medical equipment that's necessary, with defibrillator, all the oxygen kits, everything that's needed, so that the ambulance can actually go, in the traffic and goes faster than a normal ambulance. So why data is critical for this organization is because at any given moment, we know where the volunteers are. They are geolocalized all the time. We know where the ambucycles are. And when someone reports an emergency, well, the system draws like a perimeter in the vicinity of the person that needs help. And the system calls the closest volunteers, and that's where data is getting really interesting. That's where AI is interesting, is because it's also calling the most skilled volunteers according to the equipment that they have, the age of the equipment that they have, the distance in kilometers, the distance regarding the traffic. So there's a whole sort of parameters that are taken into account when the system decides which volunteers to call for the emergency. So it's about 250 algorithms, and this is one of the dispatch centers where you have data visualization for all these operators to see on the map where are the volunteers, where are the incidents, where are the motorcycles, and then they can intervene if necessary. So in numbers, in Israel, I remind you, it's a country of 8 million people. There's more than 300 volunteers, and they managed to have the response time under 3 minutes anywhere in the country. It's 2 minutes in any big city, and it's 1 minute in Jerusalem, because there's so many volunteers in that city. So it's very remarkable. It's 250,000 interventions provided a year. So that's about 700 emergencies a day, and 75% of all the emergency calls in Israel. But the most important piece of information is that it has an impact actually on the survival rate in cardiac arrest by more than 50% in the country. I'm also very happy to share with you the fact that it's operating now in other countries than in Israel. We have started in Panama, in Ukraine, in Brazil, and last year in the US, the very first unit is in Jersey City. There's 50 volunteers right now, answering 50 calls a week. Next week, we're going to graduate a third class of volunteers, so this is growing. The response time in Jersey City, thanks to United Rescue, is now 2.5 minutes, so it's a record for the country. And I think I'm going to leave that with you. Who saves a life is considered he has saved an entire world. Thank you very much.
Great. Well, that's an incredible result that we can learn from. So I think the only real example I can think of here in the U.S. is in the city of Seattle, where they trained quite a percentage of people to do CPR, but you've superseded that result by magnitude. So how do you think, and it's a wonderful project, you were mentioning how AI can actually help with this in terms of collecting the data, or how do you see AI in medicine helping this kind of a project most? How do you see that?
Well, so obviously it could be using a lot more information. For example, if that was connected to the medical records of a person. Is that working? I'm not sure. Yeah. So maybe we can envision a moment in the organization where there will be data coming even before someone describing on the phone what's going on, like using the data that's already in the medical records. Something also I haven't shared yet in the little presentation is that we're doing a lot of prediction with all the amount of data. So we know, for example, that in given areas in the summer, we know that there will be more interventions for kids drowning in swimming pool. That's a classic. We know that in winter, when it starts to rain or to snow in Jerusalem, people will more likely slide and break a leg. So there's a lot of also predictive analytics being done here.
Well, I'm a cardiologist, so I envision in the future you will actually know way ahead of time that someone's about to go down with a heart attack, and have already mobilized the team, hopefully before it actually happens when you go into ventricular fibrillation. But I can see how this can actually be even more proactive.
This community health model is the model we need to think about when it comes to solving the problem that Tim and I talked about. If you think about somebody in remote Yunnan province, miles away from a doctor, and will be miles away from a doctor for the next few hundred years, by definition. The way that my vision of where AI fits in here is that box that sits on the back of the motorbike contains a little mini GPU with a little pre-trained neural net and some kind of multi-sensor diagnostic, plus, of course, the connection to the EMR you mentioned. So the community health worker suddenly becomes
Empowered,
almost the equivalent of Mayo Clinic's top specialist in whatever that thing is, because effectively all of that knowledge is being streamed to them. And so that means that then we can focus on teaching them the data collection and the intervention techniques, and all of the kind of data interpretation and treatment planning and so forth can be kind of outsourced to the intelligence.
That's a great point. Some of you know that I'm not a big fan of the U.S. News and World Report ranking of hospitals, and I always say that the top expertise should be universalized and democratized, and so that the ranking hopefully will be a thing of the past in someday, and we should rank diseases and conditions rather than hospitals. So with that, I want to thank my very astute and experienced panelists, and then we're going to have a very, very brief break, and then we're going to bring on the first session. Thank you very much.